Pre-calc, this is 7.6, day 2, I think it is.
Yeah.
We're going to finish up working with the trig form of complex numbers. So the next group of things that we need to do is we need to multiply and divide with complex numbers. Now, I'm hoping everybody would be able to say, I could take 5 plus 3i, and I could multiply, sorry, it's parentheses, multiply that by 3 minus 2i. Those are complex numbers, right? And if I asked you to multiply those, you guys would be like, oh, 4-letter F word? FOIL, yeah. So you would just FOIL those together, gather up like terms, I squared becomes -1. We're all happy, but here's the thing, is that look at our example there, they're in trig form. If they're in trig form, there's actually another way to multiply those together, and that's using the box here, that if two complex numbers are in trig forms, so we got z1 and z2, with r1s, r2s, theta 1s, and theta 2s, they have the same format, but different angles, different radii, those things. Think back to what you did with your exponents. When you multiply their bases, you did what to their exponents? Added. When you divided, you subtracted. So it's kind of got a little bit of mixing here. That if I take my complex numbers and multiply them, I can multiply my radii together and then just add their angles. Add their angles. Done. Simplified. If I'm dividing, I just divide their radii, but then subtract the angles. Now, of course, you can't divide by 0, so you cannot have your R2 or your second complex number be 0. Makes sense. So, I would like you guys to try to do the multiplication and division on your own before we come together to actually put an answer down. Use the fact that all we're doing is multiplying and adding, dividing, subtracting. So z1 times z2 would be 2 times 2, the cosine of pi over 4 plus pi over 3 plus I, oh sorry, that was a 5. 2 times 5, right? Okay. I sine of the same exact thing, pi over 4 plus pi over 3. And then now we just have to simplify that. If I got a common denominator, what would the common denominator be? I'd have to multiply 1 by 3, 1 by 4, add them together, you get 7. So I think everybody should agree that would be 10 cosine 7 pi over 12 plus I sine 7 pi over 12. Easy enough. And again, like the question was asked, do I have to go, could I or do I have to go back to the complex standard form? The answer for this is no right now, but we could just by taking the cosine of 7 pi over 12, multiplying it by 10. And then I sine of 7 pi over 12, convert that, and then multiply that by 10. 7 pi over 12 is not one of our nice unit circle things, so you'd have to use a calculator for that. Not that big of a deal, though. Just make sure you're in radians. These can be done with degrees, okay? So be careful on that. Now, if I was doing the division, I think everybody should agree that it's 2 over 5 times the cosine of pi over 4 minus pi over 3. Yeah? So they go pretty quick once you get going here. And now you just got to make sure to simplify those. And again, I think everybody would be like, hey, I'm going to get the common denominator of 12. The first one would be a 3, the second one would be a 4, so it's 3 pi minus 4 pi. It's a negative pi over 12, right? Oh, that second one's a minus. So negative pi over 4 plus I sine. You're right. Just seeing if you guys are paying attention, is negative pi is over 12s. Almost got everything. Question is, are we done? No. Guys, 90% of the time when I ask it like that, you're not. Okay? But there's always that 10% we could have been done. But why would we not be done with this one? I don't like negative angles. We know that cosines and sines have even and oddness to them. So therefore, cosine of negative pi over 12 is the same thing as cosine of pi over 12 because the negative disappeared. Minus I sine pi over 12 because the negative will get to go out front. Now you're done. Next is DeMOIVRE'S theorem. It says that if I want to take an exponent on a trig function over a complex number. Here's the thing, guys. Look at our example. If I was going to square or cube a complex standard number form of a number, 1/2 plus 1/2 I could square that. It'd be craziness, right? Because you got fractions and you would have to FOIL. If I brought it to the 3rd power, still okay. 4th power, 5th power, 6th power, 7th, 8th, 10th power? Who wants to write that 10 times and keep on multiplying? Absolutely not. So, this guy locked himself into a closet with a candlelight 100 years ago or whatever, and he came up with this idea that if you take the power of a complex trig form number, he found out this always happens.
How do people find this?
And so r to the n power, because it's, listen guys, listen, because this is a product, and I put a power on a product, the exponent gets to go to the radius. But then they found out all I'm doing is keep adding the angle over and over and over, right? Because of that form. When you multiply them, you add them. So therefore, you're adding theta n times. So n times theta plus I sine n times theta. Very easy, quick, and efficient way to bring a power to a complex number. It's really cool. So the first thing, obviously, we need to do is we need to take that point, that complex standard form, and turn it to its trig form. Then we can actually apply it. So if I graph this, everybody agree it's in the first quadrant? Yeah? Here's a cool thing. That's a half. That's a half. Ooh, what kind of triangle would that have to be? Without even having to do the magic for it, you should look at that and say, hey, that's a what kind of triangle? It's a 45, 45, 90. So that's a pi over 4. So we know our angle. Now, can you also use that fact to find the radius without having to deal with Pythagorean's theorem? It's a 1/2 of square root of 2. Right. Because it should have been 1 square root of 2. Now, everything has seemed to be divided by 2. So yes, this becomes a square root of 2 over 2. How cool is that? It is very gnarly. So, that means we have something to the 10th power. And what is to the 10th power? It is square root of 2 over 2 times cosine pi over 4 plus I sine, I'm running out of room, pi over 4. And I need a second set of parentheses. Oh. You guys notice that there are two things multiplied with an exponent. So the 10 gets to go to the square root of 2 over 2. And it goes to the cosine sine stuff. But we have a rule for this. All I'm going to do is multiply the angle by 10. So we end up with square root of 2 over 2 to the 10th power times cosine 10 pi over 4 plus I sine 10 pi over 4. Can you guys agree with that? It's really 10 over 1, so when I multiply 10 over 1 times pi over 4, the 10 gets to go to the top. So that's why I get that. I am not going to take my calculator, and I'm not going to put square root of 2 over 2 and bring it to the 10th power. I will use exponent rules to make this happen. What is the square root of 2 really as an exponent?
1/2.
It's a half. And so what happens with that power of 10 on a fraction? It goes to the top and to the bottom. So now you got 2 to the 1/2 to the 10th power, power of power. You multiply. So this would be 2 to the 5th over 2 to the 10th. Because the square root is a half power. And half times 10 is 5. I'm not done with those yet. And then, would you guys agree that I could reduce that to 5 pi over 2? I think everybody should agree that we're not done. I could simplify the 2's, so that'd be 1 over 2 to the 5th, which actually would just be 1 over 32. Okay, so we're just going to use 1 over 32 times, do I like cosine of 5 pi over 2? Yeah. Is there a better way? Yeah. Guys, count it out. 1, 2, 3, 4, 5.
90 degrees.
90.
Pi over 2.
Pi over 2. Oh, not sine, but
Whoa.
cosine pi over 2 plus I sine pi over 2. We're done. I think that would be heck of a lot faster than taking that thing to the 10th power and multiplying. We'd still be working on probably the second or third time.
Can we just try?
You can try that in your own spare time. Okay, guys. Last piece of information for 7.6. 7.6, guys, is the nth roots. This one's kind of interesting, guys. I paid attention there, Jackson.
Gotcha.
Thank you. Guys, what's the 5th root of 32?
2.
2. So that means 2 times 2 times 2 times 2 times 2, 5 times, right, is 32.
Right.
What if I told you there were 4 more? There are 4 more numbers that when you multiply it to itself 5 times, you will end up with 32. Now, these other 4 are not real numbers, they are imaginary numbers.
They don't exist.
So, we are going to have to find them all. So if you have your complex number still, and you take a nth root, so 3, third root, 4, fourth root, 5, fifth root, z will have n distinct nth roots. So if you are finding the cubed roots, there will be 3. If you are finding the 12th roots, there will be 12. Yes, it will follow this formula. Now this formula I might let you guys have on the quiz. Now, listen on how it works because it's pretty simple here still. If I was to take a nth root of this thing, the power of a product property still applies. I would take the 1/nth power of r. But I'd also then have to take the 1/nth power of this thing. And the way this works is that you always start off with your original theta plus 2k pi, but you divide everything by n. And that's on both sides. So it's going around the circle, that k idea. And k again starts at 0 And it'll always work its way up to 1 less than the root you're looking for. So if I'm looking for the 6th root, I go up to n equals, or k equals 5, or 6 minus 1. If I'm looking for the 10th root, which is in your homework, you will have to go all the way up to 9.
Oh my gosh, Mr. Contract, that is so
What the-
long.
Okay? So, here's some observations, guys. The modulus, r, of this thing is the nth root of r. The argument of the first root is theta over n. Notice if I put 0 in for k, it's gone. It's theta over n. It happens every time for the first root. And then, this last one you can ignore for now, because I don't want you guys just to remember some obscure rule. I'd rather have you guys test it out. Get to the point where you guys start to see that there is some connection between all of these roots. And it happens to be pi over 2, or 2 pi over n, to get to the next one, to the next one, to the next one, if you keep adding it. So, here's a cool thing. You're going to be asked to graph them as well. And if you graph these nth roots of z, you will find out they're evenly spaced around the circle with a radius of r to the nth root. So if you're looking for the 6th root, you will actually, if you were to graph them on that circle, you would actually find that they are distinctly all equally 1/6 around the circle. It's pretty cool. This is our problem, guys. I want you to find the 6 roots of z equals negative 64 and then graph them on the complex plane. Now guys, what I mean by graph it on the complex plane means you need to put it back into complex standard form, a plus bi form, so you can graph them. But to start the process, you need to put it into trig form. That's not necessarily proper standard form. What would proper standard form be? What's that? Not slope intercept form. Graph it. Find theta, find r, write the form. There's negative 64. What is r?
64.
What's theta?
180.
Pi. So, the trig form we are using is 64 times cosine pi plus I sine pi. Easy enough, right? To get that part. Hopefully we've done that enough times that it's getting there. But now we have to use the formula. I want you guys to write down the formula before you dive in. So the formula is WK is equal to R to the 1 over n times cosine of theta plus 2k pi all over n, right? Plus I sine, same thing, just writing down the formula so that now I know I can use it. 64 times the parentheses of cosine pi plus I sine pi. Where theta is pi and r is 64. N is 6. So, I need to now test k equals 0 k equal 1, 2, 3, 4, 5.
It should be 64.
64. Radius is always positive, right?
That's a cosine.
You think the thing after R1 over N is
It looks like
It
It's
doesn't
a-
look like 65.
Okay, it does. That's fantastic.
I'm sorry, my bad.
Holy crap, it does look like 65.
So that's a cosine,
Holy Moses.
not 65. So that's even worse. Okay. Okay, anyways, guys. We're now going to do 0. To put 0 in, it's 64 to the 1/6 power times cosine pi plus 2 times 0k all over 6 plus I sine pi over 6. Some people are going to be a little upset with me doing that. But should they be? Why? I simplified. We know that those two parentheses are exactly the same thing. So I'm starting to, guys, make my life easier by gradually simplifying things as we go along. Also, guys, what's 64 to the 1/6 power? It's 2 in this case. 2, guys, is a very easy number. Because it's an easy number, I am now going to use 2 instead of 64 to the 1/6 power. The rest of the processes. That means it's cosine of pi over 6 plus I sine pi over 6. Is everybody okay with that? Now, because I will have to graph these, I'm going to put this back into complex standard form. So it's 2 times, what's the cosine of pi over 6?
30.
Sine of pi over 6? And if I distribute the 2, I end up with square root of 3 plus I. Now, we're going to do W1.
You making us do
Not the 6 to 5, because we do 6 of them, just like when we went around the circle several times, solving our equations. Notice, this time, I left 2, I put 2 because that is the 6th root of 64, and I plugged in a 1 for k. But when I put a 1 in for k, I end up finding out that it'd be 2 pi plus pi, which is 3 pi over 6, which in itself reduces to pi over 3. Pi over 2, not pi over 3. Pi over 2 plus I sine pi over 2. And if I wanted to switch this, 2 times, what's the cosine of pi over 2? Plus I times 1, which is 2i. And now we got to do W2. This is not hard. Does it take a while? Yeah. Now guys, as I hinted to on the last slide, there is a shorter way to do this, but I don't want you using it if you don't get it. I want you to recognize that there are certain things going on. 2 times cosine of pi plus 2 times 2 pi all over 6 plus when I sine, that becomes 5 pi over 6. So it equals 2 cosine 5 pi over 6 plus I sine 5 pi over 6. Cosine of 5 pi over 6 is plus 1/2, which would equal a negative square root of 3 plus I. And you have to do this how many more times? 3, for a total of 6 times. Now I'm going to stop there because it's just one of them will go to 10. Okay, guys, we're going to go into the graphing part. There are 3 more. Just rinse and repeat, just like this morning when you washed your hair. Now, what I'm going to do is I'm going to start to graph these. The first one is square root of 3 I. Square root of 3 is 1.73, so 1.731 over here. The next one is 2I. Well, that's just straight up to 2I. The next one is negative square root of 3I. A little bit taller there. And then there'll be another one, and then another one. There are 6 total points. All of them will be on the circle with the radius of 2. So it all works out. It's pretty cool. And they would form a circle. Whoops, wrong one. 64, where are we? To 2? Because what is the 6th root of 64? It's the 6th root of 64, which is 2, so I just carried it along. Because we found that out over here. We reduced it, and we're like, hey, that ends up being nice, so I'm just going to keep using the nice number. If it's not nice, then you would have to leave it as the cubed root or the 3rd power of whatever it is. If that would have been like 60, then I would have left it as a 6th root or the 6th root of 60 or 60 to the 1/6 power. It just turns out to be a decimal, right? So your homework, guys, is 41, 47, 51, 55, 57, 65, 74, 75, 79, 85. Have a great day.